we're going to move on to vectors in 3 dimensions. The way that we're going to do this is we're basically going to start looking at, we'll start with the component, or basically start with how to figure out components of a 3D vector. All right, so here's our 3D coordinate frame, right? We've got X, Y, and Z, and in this we have the standard, or we have the basis vectors for this as well. So this is right. So we have an I hat for the X, a J hat for the Y, and the new one, the Z, we have K hat. So these are our 3 unit vectors for our 3 coordinate dimension or coordinate axes, and we'll have our vector R here, and we'll call R. Actually, I'm gonna put this out here because that'll make sense in a minute. All right, so breaking out the components for this is a little more complicated than in 2D. And so the first thing that we're going to do is we're going to go ahead and draw a little box here, where we will project the tip of the vector down to the XY plane. Let me get rid of this real quick. And then in that plane, right, we're going to have a projected vector right here that's going to give us the image, or the image of the vector R in the XY plane. We'll talk about an angle, or a couple of angles to do this initial one. So the first one that we'll talk about is the angle from the vertical axis phi, and then the second angle we'll talk about is this theta angle, which is the angle from the x-axis to the projected line of R down here in the XY plane. Okay, and so you can think I could draw a triangle back here. So there's a triangle right here, right, and then a triangle here in the XZ plane. This one is sort of out in space, right? So this projects back to the Z-axis and gives us our height, and the other one projects back and gives us sort of the length of this one, right? So this length right here, the Z length, is equal to RZ, and then here we have RY, and then along here RX. So RZ falls out pretty quickly and is easy to do, right? So that would be magnitude of the vector, and then we have, right, the one that lies along here, so cosine phi. Okay, but now we have Rx, and this one's a little more complicated because the length of this hypotenuse right here, right, is going to be given to us by R cosine, or rather sine phi. All right, so that'll give us that. So then that means our R sine phi is the length of this line here. So that means to find the length of the x, we have to go ahead and do cosine theta. Right, so this is the length of the projected line in the xy plane, and then this is the length. This is the cosine angle here that gives us our Rx. And similarly, our y, right, magnitude R sine phi, and then cosine theta. Okay, so this is how we define our components using these 2 angle representations. All right, and then of course our vector R is then just simply Rx I hat plus Ry J hat plus Rz K hat. All right, now this is obviously a little cumbersome, right? Because you've got to be able to find this angle, sort of the tilt angle down from the z-axis, and then you'll have to project out and do this sort of analysis, and you can't really always get to this, which is why we'll actually end up not using this particular definition all that much. There'll be a few cases in the book where there'll be some convenient angles that will be given for you, and we can do this, but we won't necessarily be able to get to it directly, or get to the components using this form directly. All right, now, the way that we're going to do this is based on an idea of direction cosines. So I'm going to erase that and let's move on to here. So here is a 3D vector showing us the angles theta y, theta x, and theta z that are defined by the direction cosines. to maybe make this make more sense, let's start out in 2D. So here is our 2D vector, or 2D situation. So we've got x, y, here's theta, right? And so we have rx, and then, I'm sorry, excuse me, ry. Ry, and then rx right there. All right, and this would be vector r. Right, so in 2D, our rx is equal to magnitude r cosine theta, right, for the rx. And then we could also think of this sort of complementary angle, phi, and then we could write ry equals r cosine phi, right? Because then that makes that this triangle right here. So this is that triangle right there. Okay, so there's an angle from the x-axis to our vector that allows us to calculate the component in terms of cosine theta, and then there's an angle from the y-axis to our vector that allows us to calculate our y component in terms of cosine of a different angle. This is exactly the same sort of thought process as this. So this would be our theta x, right, and this would be our theta y. So we could back calculate this, right? So our cosine theta would be rx over magnitude r, and then our cosine theta y, right? So this would be cosine theta x, cosine theta y would be ry over magnitude r. All right. So this gets us a two-dimensional concept to our direction cosines, or these theta angles from the vectors. The 3D, unfortunately, these angles don't lie in a plane. Well, they do. They lie in a plane basically that's defined by a sort of a diagonal that runs along this axis. It's sort of difficult to visualize here. But the upshot is we get to define our direction cosines in 3D, so 3D direction cosines, as cosine theta x equal to, in this case, right, so we have Vx, magnitude V, cosine theta y equals Vy, magnitude V, and then cosine theta x, or sorry, theta z equals Vx, or Vz, magnitude V. All right, so this is how we define our direction cosines. We're going to have the components of each of the individual vectors divided by the magnitude of the vector. All right, and this, what we realize here, right, is let's rewrite this, right? So let's rewrite our v vector, right? So if we write v vector, then that's equal Vx I hat plus Vy j hat plus Vz k hat. What we've done here, right, is we've divided this, basically we've divided this out by the magnitude. And what we end up with when we do this is what's called a unit vector. All right, so v over v, this is equal to 1, and each one of these direction cosines is a unit vector. And what this means is the magnitude of this vector is equal to 1, and so this construct right here provides only direction and not length. It doesn't provide information on distance, right? Because you could multiply any one of these things, this vector basically, by any number, and you'd return the same number and scalar in terms of magnitude, but you would inherit the direction of this vector. And we're going to use this this definition of the direction cosines to help give us one of our main tools for figuring out the components of a vector, and that will be by basically picking two endpoints and then creating a unit vector. But that's our initial statement of 3D vectors, and obviously everything that we've taken before, addition, subtraction, multiplication, all that is inherited in exactly the same way.